That is because they want to get that rare gas configuration. So I feel like we've already kind of talked about this between, I think Wednesday we talked about this. So when metals lose electrons, what they do is they kick off all of their valence electrons, at least the group 1A, 2A, and 3A metals. They kick off all of their valence electrons, 1, 2, or 3, and now their new outer shell or valence shell is the N-1, okay? And you're going to see that here in a minute. Okay? So I feel like this is a little bit redundant. Okay, this slide just, I do that in some of my classes, just to hit you over the head with it. The first blue set of blue is 1A, the second set of blue is 2A, and the third set of blue is the 3A metals. Now when you get to 3A, remember, it starts with boron. Boron's not a metal because the 3A actually is part of where the Jag is. So this kind of talks about how many electrons they have. Group 1A has 1 valence electron, and it loses that 1 valence electron to form a +1 charge. Okay, group 2A, they have 2 valence electrons. They lose them both to become +2. 3A, they have 3 valence electrons. They lose all 3 of them to become a +3. Sometimes I can't remember how much you need to fill in. While I'm thinking of it, so when you're doing your flashcards, if I was doing flashcards, then I would almost set these aside. I mean, because you know what charge they form, and you know you're not going to use Roman numerals with these metals. In fact, I'll go ahead and say no Roman numerals. No Roman numerals allowed. No Roman numerals. Okay? Not optional. The problem with the whole Roman numeral thing is on the test, if you use them and you're not supposed to, you get it wrong. And on the test, if you don't use them and you're supposed to use Roman numerals for the metal, then you get it wrong. I know, it's just not fair. So sodium is atomic number 11. So if we add up these superscripts, these are 11 electrons, and these are how they're hanging around a neutral sodium atom. Sodium's a 1A. And so it actually has 1 valence electron. It'll lose its valence electron. The one to go is that 1 electron in the 3s. I think I did this the other day. So if you compare these 2 electron configurations, what's missing is the 1 electron in the 3s. That's it. We could do a similar thing for aluminum. Aluminum's 3A. So then you see, if we compare the atom with the ion, okay, what's different is those 3 electrons right there. 1, 2, 3. They're not there. Okay, so when I said a little bit ago that with the ion, the valence shell is N-1, can you see where the valence shell here is, let me choose a better color. The valence shell here is 3s. The valence shell here is, so that's 3s1, 2s2, 2p6, so that's its new valence shell.
That's the highest N.
That's the highest N, exactly. Similar here, we have the highest N is 3 here, the highest N here in the cation is 2.
So all we do is pretty much write out the, like if we were to do that and you want us to write like aluminum +3, we would just take away the last 3.
Yes. Yes, and actually that's a good point. JC's pointing out something. On your test, I will have these. You're going to see electron configurations again on your next unit exam.
Okay.
But what I think I usually try to do is I write the neutral atom, and then I ask you for the cation or the anion. So like what JC's saying is you can piggyback on the neutral, and then what you do is take off the last electrons, the valence electrons.
Either add 3 or
Yes.
I'm still getting confused with the B metals.
Okay.
When the Roman numerals apply and when they don't.
We're getting to that again. So yeah, we need to revisit that in part 3. So that's a good point, because we need to iron that down. Oops. Okay, so those were all metals. Now this is all, we're switching gears to the nonmetals that pick up electrons and form anions. So they pick up electrons to, and I love the nonmetals for some reason. They pick up those cute little electrons, and then they get to be like the rare gas at the end of that period. I just think that is so cool for some reason. Okay, so 5A elements have 5 valence electrons. We're shooting for 8, so 5 plus 3 will give them 8. So that's why the 5A nonmetals pick up 3 electrons. Okay, the 6A pick up 2 and the 7A pick up 1. So here we go. So again, this is just kind of a little bit redundant, but that's okay sometimes. Okay, the 5A pick up 3 electrons and become -3. The 6A, this is like what we were talking about in lecture or in lab yesterday. The 6A pick up 2 electrons and form a -2 charge. Now these are nonmetals. The 7A nonmetals, the halogens, pick up 1 electron and form a -1 charge. And they're kind of listed there. So again, in that stack of, Tyler said there was a lot of cutting to do with all those, like flashcards. But in the stack of flashcards, I would set these aside. Maybe, maybe not, because one of the things you need to know is how these nonmetals, you lop off the end and change it to an ID as in dog, E, IDE. So it's actually have a little bit of a name thing going on there. Okay, so chlorine 7A, it picks up 1 electron to become a -1 charge. And so you can kind of see back to back how the electron configuration works. Notice that in this spectroscopic notation, and on this slide, we're using the abbreviated rare gas notation. So we're basing it on neon. And remember how that works is chlorine is in period 3. And to do rare gas notation, we go to period 2, what the rare gas is, and that's neon. We put that in brackets. That's equal to 10 electrons. And then we say how the electrons after that are. So there you go. And the difference here, obviously, is picking up 1 electron. Where's it going to go? Well, it's going to go right there in the 3p. So instead of 3p5, we have 3p6. And then we'll keep talking about this octet thing, and you can kind of see then if you add 2 plus 6, you get your 8. Your octet. Let's pick on phosphorus. Phosphorus is 5A. It's going to pick up 3 electrons, and they're going to go right here in the 3p to go ahead and max out that subshell. So in doing so, picking up 3 electrons, it becomes charged with a -3. And that's it. All right. So, with all of this losing electrons and gaining electrons, we kind of, to get an octet, we kind of have a deal where things end up with the same number of electrons. Not only the same number of electrons, but they're hanging out in the same sort of distribution. We call those species, because they're not neutrals, because sometimes we have ions, sometimes we have atoms. We call them isoelectronic. If you want to put a little blurb up here and say vocab, you can, because this is a lovely vocab word for your next unit exam. Your next unit exam will have a vocab section, I promise. Isoelectronic. So I have an example here of things that are isoelectronic. And they're all just kind of surrounding the element neon. Basically, if you find neon on the periodic table, a little bit the nonmetals leading up to neon and the metals after neon. So the nonmetals leading up to neon pick up electrons and become negatively charged. We got those right here. These right here. These are the nonmetals leading up to neon. And these are the metals after neon. Okay? So the metals lose electrons to become like neon, and the nonmetals gain electrons to become like neon. They are isoelectronic. So this actually is getting to something that Becky raised. We have this problem with not all metals behave. 1A metals behave, 2A metals behave, and 3A metals behave. Aside from that, The only other thing you can hang your hat on, for whatever reason, are, we said, the zinc, cadmium, and silver. Okay? Yep, it's a boot. That's right. Okay? Everything else you're like, I don't know what sort of plus charge that metal's forming. Okay? So this actually gets back to writing the electron configuration. So if you're writing the electron configuration for the neutral atom and you know it's going to lose electrons, the electrons that are going to go first are the electrons that are going to go are the valence electrons. Okay? And not only that, but to get to the nitpicky, nitty-gritty, the first ones to go are going to have the highest value of L. Now, just to remind you what I mean by L. You guys probably know the S, P, D, and F by now, right? Okay, they have what we call L values, and I'll put it over here to the left. And the L values. The L value of S, you probably, I don't know if you remember, it's 0. The L value for P is 1. The L value for D is 2. And the L value for F is 3. This is actually stuff that we covered. Remember the lowest N plus L rule? And we had to like look at the subshell and assign an N plus L value. These were the L values that we assigned to those different orbital types. All it's saying is that given a chance, it's going to come from, it's going to be valence electrons, okay? And that gives you your N, highest N. But given a chance between these guys, it's going to go, the highest L first is going to be lost, and then after that. So I think, do I have an example coming up? Yeah. So we're going to pick on this one. Now, iron is an element we pick on that actually we have an Fe plus 2 and an Fe plus 3. So that kind of goes back to, that's why when you go to write out its name, you have to say iron and then parentheses and 2 or 3, whichever it is. Okay, so iron has 26 protons, and if it's neutral, it has 26 electrons. So here they are. So let's pick on, and this is just changing them so we can kind of see it peters out. We have, where are the valence electrons? What subshell? 4s2, exactly. There's 2 valence electrons in the 4s subshell. All right, so what if we have Fe plus 2? Well, we know that it lost 2 electrons, and the 2 electrons to go were these guys, right there, right? Okay, so we could rewrite this, and those electrons have gone. So those 2 electrons left. So now instead of 26 electrons, it has, what, 24 electrons, and this is what it looks like. I can't remember my notes, but it goes something like this. Now, if it is going to lose one more electron to go, now we have we're dealing with a different situation. The highest N is equal to 3. Okay, and then so we have all of these options here. Which one is it going to go from?
It's going to lose it from the 3d6 because D has one of the highest L's.
That's right. Thank you. Exactly what JC said. The L value for D is 2.
Yeah.
And so this one is actually going to go 1 more electron. But another reason it wants to do that is, remember, the whole 5. In any D-type subshell, we have 5 boxes, and it kind of likes that whole half-filled subshell too. So either way, perfect. Very good. So if you compare those two, just like JC said, which one left? The electron in the D-type subshell, where N is equal to 3. So instead of 3d6, it's 3d5. So yeah, on your next unit exam, you're going to want to be able to kind of do this. We're up to an assignment slide. I'm going to pull that up. I'm not so sure. Let me see. I want you to do that one, because I think it's irritating. Let's see. That's the one I think it is. Did a screenshot. 38 and 40. Where'd you go? There you are, number 23, untitled. Write the Lewis structure of each ionic compound. Write the Lewis model. So don't do these. Don't do these. I find them very irritating. Okay? Yay! I know, but I might make it up for it depending upon, we're going to go into part 3. There's a lot of questions at the end of part 3.
Did it say to skip the next section of sizes of ions?
Yes. And so don't do these. Don't do those. Yay! But, and like JC said, we are actually going to skip to we're going to go on to part 3 for now. Okay? So part 3, hopefully, is coming up.
A lot of pages.
Well, that was impressive. I do say so myself. Okay, how are we doing? So we got part 3 now? Okay, yeah, we're at part 3. Okay, so this should look familiar, hopefully. Okay, this is some of the stuff we covered yesterday. So ions that just a single atom that loses electrons, the metals, or a single atom that gains electrons, the nonmetals, those are called monoatomic ions. Makes sense, mono meaning one. And then, I know you guys are not looking forward to it, but we have the polyatomic ions, the ones where you have multiple atoms stuck together, like nitrate, phosphate, sulfate, perchlorate, hypochlorite. Okay, those are polyatomic ions. That makes sense. And I'm hoping we're all kind of on the same page that those things stick together. Like if you're working with them to make compounds, they don't split up. Okay? All right, cool. So this looks familiar. We actually did this figure today. You recognize the 1A, 2A, 3A metals. And I usually go 7A, 6A, 5A nonmetals. I like that because -1, -2, -3. Cool. So now this is where we're going to go around the room. We're going to go counterclockwise, if you don't mind, Jeremy. I'll pick on you first. So use your periodic table, and we're going to go around the room. So what charge does sodium form?
+1.
+1. I'm liking it. Very good. We'll go back to Alicia. What charge does oxygen form? -2. Perfect. All right. So I know Logan. I can't think of Jerry. So what charge does bromine form? -1. Perfect. All right. So back to Tyler. What?
+2.
+2 for magnesium. Yep. Becky, what about
-3.
nitrogen? -3. Perfect. JC, potassium? +1. Very good. And Austin, sulfur? -2. Perfect. And then we're back up here.
-1.
-1 for fluorine. Did I do Alicia or Jared? +2 for calcium. Very good. And then Jared?
-3.
-3 for phosphorus. We good with that? I think so. Cool. Again, this is like, well, we already did this yesterday, and we did. So one of the things you guys did yesterday and you'll do for your test is make the formula of an ionic compound by crisscrossing.
That was hard.
This is all about crisscrossing, okay? And actually, when you crisscross, you ended up, I did an example for you, but you ended up making the number of positives and the number of negatives cancel each other. That's what crisscrossing does. So that you end up, when you add them together, you get 0. And you guys did pretty good. I would say make sure that there's subscripts when you crisscross. It's easy to make those things into floaters. Okay, subscripts. Cool. This is just kind of a review. So, the word, what does the word bi mean? Two, like bicycle, both, exactly, bicycle, bi. So, we did 3 sets of stuff yesterday, and the first and second set was just where you have monatomic atoms, monatomic ions that were crisscrossed to make a formula. Okay, so those are called binary ionic compounds. All right. So let's kind of, you guys told me sodium loses an electron, forms a +1 charge. You said fluorine takes up an electron and forms a -1. So this little figure kind of shows how that looks. Okay. And so then the other day I kind of said, I think of after the sodium is positively charged and after the fluorine is negatively charged, I kind of think of this dot, dot, dot. That is my chemical bond. That is my ionic chemical bond.
When does the IDE come in again? You changed the name?
Coming up, because like if this was the compound, like you see the name of it, is it comes into the, yeah, does anybody want to,
So it can't be like hydroxide.
so it's the non-metal, and it's a single atom. Good. I think she's getting it. I see the little light bulb going off. Well, what if we're going to, and again, instead of sulfur, it's sulfide, because it's just one atom. Yep. So the first name's sodium because it's a 1A metal. So in this case, this is kind of cool. We see the Lewis dot structures of everything. I think this is kind of neat because you see sodium kind of park it over here and over there. Okay. So now in losing an electron, they become +1 charge, each of them, and sulfur and gaining 2 electrons becomes a -2, and then we have that ionic chemical bond. It's wonderful forming between that middle anion, those 2 cations. Okay, I think JC was kind of asking this morning, do you need to, if you're given the name, do you have to write the component ions? And by component ions, I just mean kind of dissecting the name, going to the periodic table and knowing that magnesium is a +2, and going to the periodic table and knowing that chloride is a -1. You don't have to write the component ions, but I think it helps. So we crisscross, okay, so we have 2 chlorides and we have 1 magnesium, and that's actually reflected in the formula. So what we did yesterday, it's all about yesterday, right? So you guys were pretty good. Make sure that in your final formula, your chemical formula of the ionic compound, you don't include the charges, okay? It's always cation, then anion. And in that third part yesterday, when we did the polyatomic ions and you crisscrossed and you needed more than 1, like sulfate, you had to put that sulfate in parentheses and then put a 2 outside to show 2 of those groups. This in italics where it says no parentheses are used if only 1 of the ion is needed. Go ahead, put parentheses in wherever you want to. Put subscripts of 1 wherever you want to. Those are kind of optional. But if you need only 1 sulfate, you don't have to put in parentheses. But you can. Trick or treat this year. Oh my gosh, who ordered that weather? Because I mean, it's really nice. I heard somebody complain a little bit because they went out and got a nice, cozy, something to wear for Halloween, and it's going to be warm. So I'm like, ah.
Usually it rains.
That's true. Usually it rains. Sometimes it's been so windy. I can remember taking the kids, and you're like, you know, being blown over. Okay, so we're going to go around again, round and round. So crisscross, and we'll start up here with Jeremy. What's the formula for that?
KCl.
KCl. I'm liking it. Okay, back to Alicia. Crisscross, and what's the formula for that?
You just like flip the numbers right, so it's AL2 and then S3.
Yep, Al2S3. Perfect. Jared, what's the formula for this one?
FeBr3.
I'm liking it. FeBr3. Perfect. Back to Tyler. What's the formula for this one?
Ag2O.
Ag2O. Very good. Perfect.
NHF4.
Becky? She said NH4F. And actually,
NHF4.
NH4. And the number of F's you need is just one also. Because you are, that's a tricky one, but you are crisscrossing, and so the number of NH4s you need is 1, and the number of fluorines you need is also 1.
Oh, because it's towards the bottom, that's why.
It's not, it's not.
Yep.
Okay, okay.
Yep. Very good. And then I have the others up there that I guess they didn't make the cut for my builds. So the next one, if you crisscross, actually the next one is an example of what I said this semester I would take, if you crisscross, I would take Cu2SO3 too. I would take that this semester. Just because I'm thinking, oh, seems reasonable. But actually you can reduce it to simply CuSO3. Any questions about those other ones? And this last one is an example of where you crisscrossed and you know that you need 2 of these HCO3 groups, so you have to put HCO3 in parentheses and the 2 outside. It's like, I know, 10 billion ionic compounds. The problem with ionic compounds is the possibilities are endless, almost. Sometimes I've done like little exercises where I pass around a cation box and I pass around an anion box and I have you pick them out, but okay. So you need to crisscross and make the formula. That's one of the things. And you also need to be able to name that darn thing. And it has a first name and a last name. The first name is the cation and the last name is the anion, whether it's monatomic or polyatomic. So we kind of, remember we did 3 sections yesterday. The first section was it was monoatomic, crisscross, name them. In the first section, all of the metals were 1A, 2A, or 3A. And if that's the case, then we say they form only one stable ion. That's where I kind of say you can hang your hat on the ion that they form, okay? And you simply give the name of the element, name of the metal. Okay, so that's 1A, 2A, or 3A metals. And then in part 2, I kind of introduced this thing, that if you look at the B elements, you're going to find silver, and you're going to find zinc, and you're going to find cadmium, and they're like in a boot shape, okay? And those actually, you can hang your hat on the charge they form too. So it's just the name. And so I like to tell students who get mixed up with Roman numerals, usually I'll go back to say, instead of saying what you do use Roman numerals for, to me it's easier to say what you don't use Roman numerals for. And those are ones you don't use Roman numerals for. So for those metals that can commonly form 2 stable, I don't usually read my slides, stable cations, okay? Remember with iron, we did an Fe+2 and Fe+3. So basically though, and sometimes students don't get this, but I'm saying anything that's not 1A, any metal that's not 1A, 2A, 3A, nor is it silver, zinc, and cadmium, if it's not one of those, it can form more than one stable cation form. Then you have to use Roman numerals when you name it, not in the formula. All right. So to kind of emphasize this again, like I said, to me it's easier to say when you don't use Roman numerals. Don't use Roman numerals when it's 1A, 2A, 3A metal, or if it's zinc, cadmium, or silver. And was it yesterday that I said zinc has a +1 charge, no, zinc has a +2 charge. Zinc and cadmium +2, and you can kind of see they're up +2, then go over 1, it's +1. Okay? So otherwise you have to use Roman numerals. All right, so we left off with JC. So all you got, well, not all, you have to do two things. You have to kind of know that maybe Ca is calcium, and then you need to know, do I use Roman numerals or not? So that's right, you don't. You just use the word calcium. And you might need to find these on the periodic table. So back to you, Austin. So potassium. Potassium is a 1A. Do you use Roman numerals or no Roman numerals? Yes, no Roman numerals. No Roman numerals because it's 1A. So just the name is just simply potassium. And then we're back up to you, Jeremy. Barium. Find on the periodic table, do we use Roman numerals? No. No Roman numerals, so it's just barium. How about Alicia? Yes, Roman numerals. Yes, Roman numerals, lead 2, perfect. Jared, what would the name of this one be?
Lead 3.
Not lead 3. Lead 4? Yes, lead 4. Yep. And if you're like me, you need to kind of make sure you review how you do Roman numerals a little bit. All right, we're back to you. Tyler, how about sodium? No. Nope. The name is simply sodium. Aluminum? Becky? No, it's a 3A metal, so its name is simply aluminum. On to you, JC. Cadmium? No, that one threw me off a minute. Why don't we use cadmium?
Because it only has 1+.
Right. So it's just simply the name cadmium because it's with cadmium, zinc, and silver. Now we're back to you, Austin. What do you think? Magnesium?
No.
Correct. It's just the name magnesium. And I don't know why this was on there. Yeah, ammonium. I have no idea why that would be on a Roman numerals one, but there it is. No Roman numerals for NH4+. Very good. It's looking good, guys. I don't think we're going to do that. I think we have. Do you guys want to? Do you guys have these to fill in? Seems like I just got kind of tired of the whole thing. So on that whole list, there's only 2 that you don't use Roman numerals, and that was zinc and silver. Everything else you do use Roman numerals. But I guess I would say, again, there's an outlier, just like ammonium was an outlier on the previous. It's like one of these did not like the others. Well, one of these things is not like the others. To me, this guy right here, which is the most irritating polyatomic ion I know. Remember I said it sticks together as a unit, it doesn't divide. So this is actually Hg2. It cannot be reduced to Hg1. Hg2 running around with a +2 charge. And it's called the mercury 1 polyatomic cation. Don't blame me. I think I would have called it something else. Okay. All right. So again, it's like, dang, we just covered that, right? Okay, so on that one sheet, I had you put for polyatomic anions, I had you add 2 polyatomic cations, positively charged polyatomic ions, ammonium and the mercury 1 polyatomic ion. These down here are just kind of isolated because they don't have oxygen. So Cn-1, it's in your stuff to memorize. That is cyanide. SCN-1 is thiocyanate, and in one case, 3 iodine atoms get together collectively with a -1 charge, and it's called the triiodide ion. So this kind of gets to what Becky we were talking about. The idea of if you have monoatomic anion, what does that mean? Mono meaning 1 atom, anion. So you're talking about your nonmetals, yeah. You lop off the N and replace it with IDE. So we're gonna, who do we end up with? So we end up with Austin, no, you kind of answered ammonium, but go ahead and answer this one. So O2 minus, what's the name? It's not oxygen, it's
Oxide.
Oxide, very good. Okay, Alicia, N3 minus, it's not nitrogen, it's nitride, very good. See, that's where I feel like I'm being rude, like nitride, like I emphasize the D, okay?
But, okay, and it doesn't matter if it's 2 or a 3 or just it just has to be a minus charge for the IDE.
It has to be one atom. So
Single atom.
notice the single atom, this is just a single atom, so
Right, I
there's
got it,
one.
I got it.
Yep, okay, good. Okay, so we're on to Jared, S2 minus, not sulfur, it's sulfide, very good, I'm liking it. So Tyler, it's not chlorine, it's chloride. And if you're like me, I kind of always forget is where the H goes in chloride. So don't, if you do that, you're company. So Becky, instead of hydrogen, it's
either hydroxide or hydride.
the latter. See, but hydroxide. Yeah, hydroxide is OH minus 1. I was trying to think hydride is right. Hydride.
Oh, it's one of my guesses.
Yeah, I can see where you're just gonna have to. I see where you're coming from there. JC, it's not bromine, it's bromide. Very good. And Austin, it's not phosphorus, it's phosphide. Very good. And then we're back up to Jeremy. It's not fluorine, it's fluoride. They put in our toothpaste. And on to Alicia, it's not iodine, it's iodide. Perfect. Excellent. So then these are the hints that I gave you. We have a lot of oxy anions, which just mean polyatomic anions, which just means you have an element, you add oxygen to it, and it runs around as a polyatomic anion.
There's our hydroxide.
There's your hydroxide, yeah. So the hints I gave you yesterday, and sometimes I use, oh, I ate too much oxygen. That means I'm gonna actually have extra oxygen compared to my ite. I don't know if that works for you. So the examples, I've got some examples here. We have 2 sulfur polyatomic oxyanions. So sulfur combines with oxygen in 2 different scenarios. We have SO3, 2 minus, and SO4, 2 minus. The one that has more oxygen, SO4, 2 minus, ends in an ATE. It ate more oxygen. Okay? And then picking on nitrogen. But this is a good example because even relatively speaking, you know, the nitrogen oxyanions have a -1 charge instead of -2, so it's compared to sulfur. But it has 2 forms, NO2 and NO3, both with a -1 charge. The one that has more oxygen, it ends in ATE.
Does it matter if you put the minus sign on the right or left side of the subscript?
It really should go in the upper right-hand corner. The one thing that I don't know why I do this, but sometimes it's, instead of saying 3 minus, it's -3, so you can do that. But yeah, that should go up there. And then we have these guys, these halogens, that they have 4 different forms. You're like, are you serious? Okay, so the good thing about them is they follow the pattern. And I kind of said yesterday, I think of it this way, and it works pretty well, that I said you kind of have your ites and your eights kind of in the middle. And if it's a little less than ite, you have to add a prefix. And if it's a little more than h, you have to add a prefix. So that works pretty good, I think. Like, how far are we from that assignment slide? We got it. What's that?
14
Where they
slides.
use paper.
Hyper, I don't, yeah. Yeah,
Instead of perk.
I agree. I agree. So, and then are we good with this? Here's my little hint with hydrogen, and I think I pick on phosphorus here. Oh, no. I pick on kind of an assortment there. For each of these groups, do you have these? No, they're already. For each of these groups, you already got them written down. Notice that when we bump up, adding a hydrogen, it bumps up the charge, or it takes the charge down one. So I'm going to skip all these. You're like, are you serious?
Oh.
Because we're ready for an assignment slide.
I feel like I had a dream about it.
Yeah.
Deja vu.
So skipping ahead to the assignment slide, let's take a look at what those look like. So that last one, and it's a Friday, so you got all weekend to work on it.
I'm gonna work on it at intermission in my musical.
What did I
So
say,
if you come to the
23?
play, you can know what I'm doing at
Oh, that's right. Everybody come to Adam's Family
intermission. Yeah.
tonight at Grand.
Tonight's the opening night, and then we perform tomorrow at 7:30 and Sunday at 2.
Okay,
Where?
The Grand they're putting on like.
that's cool. I think you're going to be wonderful.
That's gonna be.
Okay, so yes, do mix this with that. So there's a lot here, but it's great. The more you do it, do you want me to? Yeah, the more you do it.
Let's do one together.
Or is that the last?
We did. We did cover it. Yeah. So, but what I was thinking was, this is one assignment that if you want a little extra time, this will either be due Monday or Wednesday. How's that?
Okay.
It's my first time. And if you have any questions and that sort of thing. So this is due Wednesday.
Okay.
That musical is.
Because there's a lot here, and I'm not going to go through each of them, but you can kind of see it's what we've been doing, okay? So you kind of see those and these, okay? There's quite a bit, and that will be due on Wednesday. Hey, don't forget to go out and instead of doing this, go ahead and evaluate me online. Say,
Yeah, she did the survey.
So anyway.
She's
So.
awesome.
No, be honest and